Bioinformatics.
Okay, so this is going to be a video where I walk through the second lab, which was on the Fastq, Fastq, Fred scores, and quality control. Again, these videos are not intended for you to watch start to finish. This is more a resource for if you had areas that you stumbled or you would like to see how I did it, or maybe some other things that I said along the way. So what I have here is myself already logged into my Amazon Ubuntu server. It's a brand new server that's just starting this lab. So I don't have anything else installed other than what you're watching me install. So first step, we need to install a couple of the things that we'll be using throughout this lab. We're going to be using Conda to install most of our packages throughout this semester. So we're using Conda and we're telling it that we want to install, and we're passing the argument -c, which says I want to use a specific repository for you to look for this piece of software to download. And many of the things that you'll see we download and install come from the repository Bioconda. So we're going to install SeekKit. It's going to take a minute. It's going to ask us a yes or no if we want to proceed, so we can say Y for yes. Go ahead and install these things. If it looks like it's happy, so don't overthink anything here. We'll go down. We're going to do the same thing for FastQC. Rather than retype all that, I'm just going to press up, and I'm going to backspace, and I'm going to say FastQC. We're going to go ahead and install that as well. And now we're going to go ahead and move down into the lab. By the way, beneath both of those both of those installations, I have links to where you can read more about those software if you so choose. So one of the first things we do in every lab is we want to make a folder for us to work within. So if I type ls, you'll see there's not much going on in my home directory. So I'm going to make a directory and I'm going to call it lab2. And I'm going to cd into lab2. Okay. So first thing we need to do is we need to download some data. Now, there's a variety of ways to get genomic data. In this first way, they're actually housed on a different website, and we're going to use wget just like we did when we did our server initial setup. Wget just downloads whatever file is at a given location. And so I'm going to copy and paste all of these. Again, although I tell you not to copy and paste too much, for long things where it's easy to put in typos, it's okay to copy and paste. So we're going to copy and paste all these in, and you're going to see a little download bar happening for each of them. When you copy and paste multiple lines, typically the last line will actually end up right there in the line as if you typed it and not automatically execute because there wasn't a return at the end of it. So we're going to hit return one more time for that third one, and it's going to go ahead and download. Okay, so something I always do when I download things like this, make directories. I always like to type ls pretty frequently and just see what's in here. So it looks like we downloaded all three things. If you notice, they end in .fq and .gz, and then .fn.gz and .faa.gz. So these are different types of files, and I kind of wrote about them up above. The .fq is just a shorthand way of saying .fastq. So we talked a little bit in the lecture about FastQ format. .gz is a type of compression. So these are compressed right now and not actually human viewable. You could confirm that for yourself by saying let's head duplicated reads, and it's a bunch of garbage because this is a compressed format. So and then we've got .fna, which are actually our assemblies of our raw sequence reads, and then we've got a translated amino acid sequence as well in the .faa. So we installed SeekKit. Now this allows us to kind of bypass the actual compression and actually learn some things without having to go through all the compression format. So this can sometimes be kind of nice. This is called kind of parsing. So we're parsing through our compressed data and just looking at a subset of the output. So we're going to SeekKit stat, and I want to look at the stats of all of these. And so this is where wildcards are really helpful. Something that all of these have in common as far as an easy identifiable pattern is that they end in .gz. So we could do wildcard.gz, or we could do them all separately if we wanted to, and hit enter. So here we can see a nice output in a little tabular format of the file names, what format they are, so FastQ, and then FastA is the format for both the assembled reads and the assembled amino acid sequences. You can see the number of sequences here, the total length of bases, and then the minimum length of any given read, the average length, and then the maximum length. So these are kind of nice informative things to be able to quickly get from your data. We can also modify ls to tell us a little more about the size of these files using ls-l. And so here we can see, again, permissions like we mentioned earlier, but we can also see when these were added, as well as the bytes that they take up. But computers are so big now, no one thinks about file sizes in terms of bytes, so we could modify this one more time and tell it that we want to look at the file size in megabytes. So here we can see that one is 2 megs, one's 61, and one's 38. So these are very, very small kind of example data sets as far as genome data go. Okay, lastly, we want to actually uncompress these so we can start working on them. So to uncompress .gzs, we're going to use gunzip. So gunzip is as simple as just passing that command and then the file names that you want to unzip. So we're going to gunzip, and we can do either one at a time. So we could do duplicated reads and tab it out, or we could again use wildcards to our advantage to save ourselves some time. .gz, and hit enter, and they're going to start to uncompress now. Okay, it looks like it's done. Let's hit ls and see what happened. There you go. You see they're no longer ending in .gz. They are supposedly uncompressed. Now, something important to mention is that just because a file has an extension like a .gz or a .word, .doc or .excel, that doesn't actually mean that the contents are any different. I could rename any one of these to .docx or something like that, and it's not going to change the contents of the file. And so while you're used to on a desktop thinking about the extensions of a file being, intrinsically tied to what's within those, the type of content it is, they're almost, in a command line interface, just an indicator of a placeholder for kind of reminders of what type of file it is, but it's not required. Very few applications require the ending to be a specific thing. They care more about what the format and the contents are. So that's why you can have .fq and .fastq as interchangeable. Well, let's look at one to make sure that it's human readable now. So let's head duplicated reads .fastq, and yep, now we actually have letters and numbers and all sorts of good stuff. Okay, next we're going to talk about Fastq manipulation and quality control. This is an important first step when you first get all your raw sequence data. So understanding the format of a Fastq file is important. There are 4 lines to every Fastq sequence, and you can have many sequences in one Fastq file, but they're always in that format of 4 lines per sequence. The first line will always begin with an @ symbol. So here, if we look here, we can see the first line of a sequence, @ and then some information. This could be the name of the sequence, the length of the read in this case. It can also be positions on the flow cell of an Illumina sequencer. The second line is the actual sequence. So the actual nucleotide sequence right there, A, T's, G's, and C's. Then there's always a spacer line. The third line starts with a plus, and it can have more information. It could be just a plus, or it could be a duplication of the first line. Doesn't matter. And lastly, is really one of the most important lines, is this quality score line here. So there's a bunch of letters here. It can also have numbers and exclamation marks and @ signs, a bunch of different ASCII characters. And these are all placeholders for those Fred scores that we talked about in lecture. We talked about this Fred table in lecture. I'm not going to go over all that again. But I wanted to give you a chance to explore how to convert very quickly and easily to Fred scores using kind of those ASCII characters and some really basic coding in a language you probably haven't used before, which is Python. And part of this is that I want you to see that to kind of demystify the use of code to do things. Many lines of code are just tools, particularly how we use them in bioinformatics. You don't have to be an expert in the language to understand the purpose of a line of code and to substitute parts in an intelligent manner and repurpose them without being an expert coder. So if we wanted to find the ASCII value, again, remember this chart, every character has an ASCII value. So we could go down to the ASCII value of an exclamation mark is 33, or for A is 65. So we could use Python. And again, I'm not expecting you guys to learn Python here. This is just an example of how you can do things. So if we want to see the ASCII value of A, there's some code that will do it. What if I wanted to find the ASCII value of B? Well, I could just hit up, and the only thing I need to change here is A to B, right? If I asked you Z, you could probably figure that out. We can also use Python to do the opposite. We can give it an ASCII value, and it will pass us the character. Now, just as we're learning by doing, one thing you'll notice is that when I'm passing these characters, when I'm looking for characters of numbers, 65, versus letters, I'm actually putting letters in quotation marks. This is because letters and words are what are called strings, and typically you want to pass them as within quotes as a way of indicating that. Numbers have values to them, and so you typically don't need to put those in quotes. Okay, and so if we execute that 65, we see that it's A. I bet if we were to do 66, it would come back as B, right? Okay, so that's exactly what we would expect. Now, remember, we mostly see things in Fastq files now being coded in FRED33. Now, this is basically that scores, the FRED scores, are the ASCII value minus 33. So we can use this same code that we just used and add in a minus 3 to actually output out what the FRED33 score should be instead of just the ASCII value. So this is the ASCII value of A minus 33, and it's 32. So if I were to ask you to look at the first line of that Fastq file and look at the quality scores of the very first sequence of maybe the first 5 bases and tell me what the FRED scores of those were, hopefully you'd be able to repurpose this and do it with a little bit of kind of, trial and error. So to do that, I would head that Fastq file, and if we look at what the very first sequence is, so we go down to that 4th line where the scores are, well, the first 5 are pretty easy because there's only 2 possibilities. There's C's and F's. So we could go here and go, okay, what's the ASCII score of a C? It's a 34. And what's the ASCII score of an F? It's a 37. Many of our cutoffs are actually at 30, so these are both good scores. We could confirm that with ourselves, though, if we wanted to go a little bit crazy, and this is probably a little far and beyond what you need to even worry about right now, but we could actually remember that FRED scores are calculated as minus 10 times the log to the 10th of the P error. So we could actually add that into our equation here, and I'm going to copy and paste this one just to make it nice and simple, and see what the p-value of calling that base where the 3rd line or the 4th line has an A, what the p-value of that would be. So basically we're looking at a very small p-value, 0.0006. We're very confident in that base based on that quality score of A. What about F? What's the confidence of things that are scored with an F? 0.0019. That's another good value. Now, what about an exclamation mark? That's a 1. That's the very bottom of our, that's basically we're 100% certain we've got it wrong. Okay? So that's how these FRED scores are calculated and used in kind of the trimming that we're going to see here later, where we go through these raw reads and decide which bases to keep and which reads to keep based on how confident we are in the sequences being called correctly. Okay, next I want to talk about how we actually visualize large sequence data sets very simply, just to look at kind of the overall quality of how our sequencing did. So we're going to be using FastQC, Fast Quality Control, on our Fastq file. So let's go FastQC, and it's a duplicated read.fastq, and that was very quick. So what we get from this is we get, if we type ls, we get both a zip that contains a bunch of kind of images and stuff, but we also just get this nice simplistic HTML file with the name of the sequence _fastqc.html. Now this, we can't open HTMLs and look at them within the terminal, but if we're able to pull this down to our local computer, we can look at it with a browser and see some nice figures. So I already submitted a video for how you can use CyberDuck on Mac, so if you haven't seen that yet, go ahead and look at that video. If you're on Windows, you're already using Xterm, and if you look to the left of where you're typing all your commands, you'll actually see a file browser set up where you can browse through your server and right-click and download this HTML file. So using CyberDuck, I'm going to download that really quickly. And I will open it up so we can look at it. Okay, so I've got this pulled up, and what we can see here is we can see a box plot for all of our reads. And so if you're interested in how many reads, there's 15,000 reads in here, and the length of the reads are 101. And so all these reads for about 101 base pairs. So this is, if we're thinking about 101 base pairs in a row, we've got a box plot for every single position from start to finish where we can look at what the average quality score is. So here's these Fred scores. Remember, typically above 30 is pretty good. Once you get below 30, you start getting into questionable, and below 20, you don't want anything to do with it. And so here we can see all of our sequences are at the beginning at 32 at a minimum or so, and going all the way across. In general, we don't see any of our bases in any of our 15,000 sequences that dip into questionable areas. So these bases are already, these sequences are already probably been trimmed already, or very high quality sequencing. We can also scroll down, and there's some other graphs that we can look at. We can look at things like GC content. We can also look at how many ends, which are uncertain bases. Because our quality is so high, we don't have any uncertainty, so that's going to be 0 across the board. One of the ones I really like to look at is the sequence length distribution. This is where you can, let me pull this up, where you can see that the distribution of, are most of my reads short, or most of my reads long. Now, something about Illumina sequencing, prior to trimming, all your reads are going to be the same length, whether it's 100 or 150 or 300, depending on what kind of sequencing you did. But other types of sequencing are more variable in length. Something like PacBio, you're going to get different lengths of reads, and something like Nanopore. So this will sometimes be informative and sometimes not. Typically, after you do your first round of trimming, you want to look back here and see if you've got lots of really kind of high quality but short reads that are too short to be useful, or if most of your reads are kind of on the longer side. So you can always come back to that. Scrolling down, you can see whether there's sequences that are statistically overrepresented. Whether this is helpful to you depends on the type of sequence you're working with. If you're working with RNA sequence data, you would expect lots of overrepresented sequences from highly expressed genes, so that wouldn't be informative at all. And then you can also look at adapter content. Typically, when you get your sequence data, the adapters that are sequenced at the edges of your reads are already accounted for and trimmed off. Sometimes you end up with rough sequence data where adapters are left on. And so you can look here, and Fastq is an older program, and so it doesn't have all the most recent adapters in it, but you can see many different adapters if there's an enrichment in certain areas. Okay, so now that you have a little experience looking at Fastq and how to use that to investigate the quality of your raw reads, we saw some examples of high quality reads. Let's take a look at some examples of a little bit lower quality before we start to talk about how to deal with that low quality. So let's get some data of varying quality. Here I'm having you do an alternative way of downloading from a URL. This is the equivalent of wget. This is curl-big O, where it's the big O argument stands for outputting the same file name, basically. So we can copy and paste this, and it will download this compressed file of several different sequencing runs. It's not very big. It's only 120 megabytes. And what we can do now is unpack it. So let's take a look at it. Now, this is a different format, tar.gz. We haven't experienced that yet. So that gunzip might not be the right ticket. This is a good chance for you to practice using Google to kind of answer your own questions. If I was curious, how do I uncompress a tar.gz compression file? Well, the first thing I would do is Google it. And so I've actually already done this. And if we look here, tar.gz extract, really it pops up quite quickly. Many of these kind of common things people ask, you'll see quite often. So to unpack a tar.gz file, you can use the tar command from the shell. And these are the arguments we want for extracting, because you can use the tar command to also compress. So we want tar-xzf. So let's go ahead and hop back to our terminal and go tar-x, probably for extract, right? xzf, and then our sequencing platform data file. So this will take a second to unpack. Now, we also could go man tar, and we could go through this whole file and come here and look at what these different things would actually do for what we want. But sometimes Googling is just a quicker and easier way. Okay, so let's ls. And what do we have here now? We've got a bunch new files that popped out of this. So we've got this pacbio.fastq, iontorrent.fastq, and illumina.fastq. What I would like you to do as a part of this lab that you should have already done is I would like you to use the skills that you just developed in FastQ-seeing to look at the quality of both the Illumina data as well as the iontorrent data. And so I'm going to go ahead and do that, and I'll fast forward once I've got them on my computer and we can just look at them really quickly. Okay, so I've gone ahead and FastQ-C'd and pulled these files down for the reports to my local computer, and we'll just quickly look at them before we move on to the next part together. So our Illumina data, small data set, only 5,000 reads. Pretty good quality, not quite as good as what we were looking at earlier with the duplicated reads file. The early bases in the read, perhaps the first half, pretty much all the reads in the data set are above 30 quality for each of those base pair positions. Once you get to the last half of the base pair positions, we start to get some outliers or things at the bottom of the first quartile that start to dip below a quality that we can really trust. And so this would benefit from some trimming to cut off the tail of these reads and either consider keeping those or ditching the ones that actually have those low quality tails on them. Everything else looks pretty good. You can scroll through this yourself. But what we'll dive into next, just to see an example of really rough raw data, are the iontorrent data. And so here, a couple different things are going on. Here we have 10,000 reads. Unlike the Illumina data, we actually have a variable sequence length. Iontorrent isn't always the same sequence length, unlike Illumina. And so here we've got reads that are as short as 6 base pairs and reads that are as long as 555. And so that's why once we get towards this tail end, we have some pretty poor quality because the quality starts to go down as you sequence further and further out. But in general, the quality of these look quite low. It's really only kind of the top 75th percentile of any given reads base pair position is really above that 30 quality score that we're looking for. So I would imagine if we quality controlled this, we'd lose a huge chunk of our sequence data. So you can scroll through here as well, and you can see some of the noise that gets associated the further you sequence out. Okay, so that's just looking very quickly at those data sets. And so next, we're going to talk about how to trim those data. Okay, so we're ready to think about trimming or quality controlling our raw sequence data. And to do this, we're going to use a very common program called Trim-O-Matic. Now, Trim-O-Matic lets you trim in a variety of ways. It lets you trim using either a sliding window, or you can trim specifically for adapters. Now, we talked about what adapters were. Those are parts of the sequencing process that can sometimes be left over that look like sequence data, but are actually man-made, if you will. And so if those get left on the beginning or the ends of your reads, you would like to cut those off. And those are conserved sequences that we can search for specifically and remove if we find them. The other issue is a sliding window, which will look for regions of low quality and decide whether or not to cut off the read starting at that area. And so the way that works is for any given read, say you have a read that's this long, we'll take a window of whether it's 5 bases, 6 bases, and we'll start at the first 5. And we'll ask ourselves, what's the average quality control or quality score within that window of 5 bases? Based on what cutoff we set, say we set a cutoff of 30, if the average is above 30, we shift over 1 base. What's the average now? Above 30, we shift over 1 base. We go until it dips below the quality score average that we want, and if it dips below that, then we cut off the read at that point and ditch the tail. So you can end up with quite short reads if you have regions of low quality towards the middle of your reads. And so Trim-O-Matic also allows you to set a minimum length for keeping reads. So if you cut off all but the first 5 bases, you could drop it if you said my minimum length is 6 or 30 or 50 or 75. So Trim-O-Matic's quite flexible. Now, to install it, I've actually already installed it on this server right before I started this video, but you are familiar now with using conda install from the Bioconda repository. So go ahead and install that. And next, we've been looking at really small data sets, and they aren't always as optimal for issues of cleaning and trimming because you're looking at a really small sample size. And so we'll work with this Illumina data set really quickly, but then we're going to transition to a real size data set. So as just kind of a nice, easy example, those Illumina data are already pretty clean. They just had kind of that poor tail at the end. We'll go ahead and run Trim-O-Matic on them and see kind of how it might look a little bit different. So Trim-O-Matic, we're going to use single end because we're only giving it one set of reads. Illumina.fastq. Now the output we need to give is the second name, and I'll show you in a second how you know that that's the format at once. I'm going to call this Illumina.trimmed.fastq, and then we need to tell it what we want it to do. Sliding window, double dot. I'm going to say we're going to look at a window of 4 bases at a time with a minimum quality score average of 30. So if we hit enter, what do we see? We see that we started with 5,000 reads. We dropped about 850, so that left us with 83% of our total reads and dropped about 16%. So what I would like to do now is let's go ahead and FastQC that Illumina trimmed and drag it onto our computers and take a look at it. So one sec while I pull that up. Okay, we're back and I've got the trimmed Illumina data FastQC report. So here's the original pre-trimming, and as you recall, towards the end of the reads, we had some kind of low quality reads, and we wanted to see if we could get that cleaned up. So here's what it looks like after our trimming, after we dropped about 15% of the reads. Pretty much everything is maxed out at every single position. There's not a single base pair on any given remaining read that's really below 32. So that's really nice. Now we have kind of a nice bulletproof data set. Again, it's very small because this is an example, but our trimming worked, and this looks quite nice. Okay, so that was an example of using quality control trimming. Let's talk about how to deal with adapter content now. So in order to look at adapter content, let's download some reads that have some actual remaining adapters. And let's look at a larger data set, a little more close to something we would actually be using in a real experiment. Now, to do this, you're going to install the SRA tools. This is to interface with the short read archive, which we'll talk about next week. It's a place where when you publish papers using next-gen sequence data, you can make your raw sequence data available in a repository and easily accessible using the SRA tools function Fastq dump. So I've already got that installed, but let's go ahead and Fastq dump this SRR 519926 accession number. Now this is going to take maybe 5 minutes or so to download, so I'll come back when it's done. Okay, so my Fastq dump of that accession has completed. So if we type ls, we can see, because this was a paired in set of data and we asked it to split the files, we've got our forward reads and our reverse reads signified by the _1 and _2. From here forward, we're just going to work with the forward reads, the _1 just for simplicity's sake. So go ahead and FastQC these on your own and take a look at the adapter content on these. And so I'll do the same thing and we'll look at it together. Okay, so hopefully you were able to FastQC that. And so looking at what I'm looking at, well, here we're dealing with a much larger data set. We've got 40,000 reads now. Still a small data set, but much larger than you've worked with thus far. Front half of the read, pretty good. Towards the end, it starts to get pretty bad. Now, why might that be? So if we scroll all the way down here, ignoring all the other read information, and we look at the adapter content, we see that in red, towards the back half of the read, we start to see up to 10% of our reads containing some semblance of what FastQC thinks is remnants of adapter sequence. So not real biological sequence data. This is that artificial sequence that has been added on to help with the sequencing process. And so we need to figure out how to get rid of that. And by getting rid of that, we'll probably clean up our data a little bit too. First thing you need to know is the actual sequence of the adapter so that you can tell Trim-O-Matic what to search for. I'm going to save you the trouble of trying to search for what the TrueSeq adapter sequence is. It is this sequence right here. And you could make a text file and import it into your server, or we could just kind of use some shell scripting or shell commands to kind of make a little file for us. So here I'm going to echo Illumina. And so if I do this and actually just this part, all it does is it prints what I wanted it to the terminal. Now, you remember from our intro to shell that you can actually redirect things that go to the terminal into a file. So we're going to redirect this line of text into a file that we're going to name adapter.fa. Okay, now if we were to head adapter.fa, we see that it starts with that Illumina line. Now let's add a second line. This time we're going to redirect with 2 carets, and that's going to not overwrite the file, but just append to the end of it. So we should just be making the second line the sequence. And the reason I'm making it formatted like that is because that's what Trim-O-Matic wants. You could go look at its webpage and their manual if you don't believe me and you want to look at it for yourself. So let's go ahead and look at that again. So this is exactly what we want. Now we have all the information that we need to give Trim-O-Matic. So let's go Trim-O-Matic, single end, because we're just going to work with one of these. We could do paired end and give it both, but it's going to be a much longer command line. Oh, let me show you this real quick. So how do I know to put the input and the output in this format? Well, if I do Trim-O-Matic without feeding it anything, it gives you some suggested uses. So for single end reads, it gives you all these things that you can put in as options. So things in brackets are optional. Things within the greater than less than sign are required. So you can provide it with some options, but then you need to provide in this order the input file name, the output file name, and what trimmer stuff you're going to do, like sliding window, adapter trim, things like that. So let's go Trim-O-Matic and following that format, single end. We're not going to give it any of these optional arguments. We're just going to say we want that srr_1 file .fastq, and we will call it the same thing, but we'll call it clipped, since we're going to clip the adapters. Trimmed we'll reserve for quality control. .fastq, and we want to do the Illumina clip, tell it the name of the file, and give it its quality settings, and hit enter. So we dropped about 11% of the reads, or around 46,000 out of the 400,000 that we started with. And so that's a good number of reads got dropped. Now, how did that make the overall sequencing quality look? Let's FastQC it again. So go ahead on your own and FastQC that trimmed file, and we'll look at it here in a second. Okay, so right now I have the unclipped version up, and again here this is what that looked like, and here's what the adapter content looked like. Now, if we look at our clipped version, well, we still have some low quality at the end. We're probably going to have to do some quality control as well as adapter clipping. But if we go back and forth, we did clean up a little bit of this. You know, it has shrunk some of those whiskers up a little bit, but it's still not great. But let's see if it did what the goal was. Well, if we look at the adapter content, there's none left. So now we've got a nice adapter-free set of sequence data, which is what we want. So now what we should do is we should put it all together. Now we could work with this clipped data set and trim it now, or we could just clip and trim at the same time. I prefer to do it all at once. I think that's the more efficient way to do it. And so here I asked you to try and figure out how to do that on your own. And so if you weren't able to figure that out, all we're going to do is we're going to repurpose what we've already done. So we'll just press up a few times. to get that adapter trim-o-matic set up, and we'll change the output name. So we're still going to start with the same input here, and this time we're going to want the output to be both clipping and trimming. So let's call it clip and trim maybe. And then we'll add the Illumina, the sliding window trimming here on the back end. And so sliding window, if you didn't remember what it was, you could scroll up here to where we used it previously and just repurpose this little piece of code. Okay, and now hit enter. Okay, this time we dropped about 72,000. And so a little bit more restrictive, but we're going to FastQ this clip and trim and look at kind of what our final cleaned up read set looks like. Okay, we're back. Just again, refresher, here is what the raw ones look like, really dirty. Here is with the adapters trimmed out, a little bit better. Here's with both the quality control and the adapter trimming. Now we lost about almost 20% of our reads, but I think you would agree with me that it's much better to have this perfect looking sequence data set with slightly fewer data points basically, than to keep all that garbage. Because many analyses, we like to say garbage in, garbage out. So it's nice to start with good quality data. So this is all nice. We now have a really nice, clean Fastq file. What we can do next is we can go ahead and ditch the Fastq format. Remember we learned that Fastq format is 4 lines for every sequence. Fasta format, or Fasta format, is 2 lines. It's just 1 line for the identifier, the name of that read or sequence. And the second line is the actual sequence itself. No longer do we need the quality scores because we've determined that all of what remains are high enough quality that we trust that those bases are what they say they are. So we effectively can cut our file sizes in half by ditching those last 2 lines for each format. So let's go ahead and install the Fastq toolkit, and we'll use that toolkit to convert Fastq to Fasta. So we'll conda install from bioconda the Fastq toolkit. We'll hit yes. And within that toolkit is the Fastq to Fasta function. And so we will go ahead and use Fastq to Fasta. And our input, let's just do this on the Illumina data so it will be nice and clean, or nice and quick because it's a smaller data set, but you could do it with the one that you just finished working with as well if you wanted to. So we'll go illumina.trimmed.fastq is our input file. Our output file is illumina.clean. I just like to call it clean because we've cleaned off all the quality scores. .fa now, just so we can remember. Again, you could name this .blah and it would still function the same. But by convention, let's call it .fa for .fasta. Okay, so didn't kick back any arguments, so let's go ahead and head that illumina.clean.fasta. Okay, here we go. So we've got very short reads and read names here. So here's the read name, here's the sequence data. Now, what we can do is we can try and make this a little bit nicer and shrink the file size even more. If we don't need all this information here, we can also use Fastq to Fasta's other options to simplify that a little bit. So most programs, if they're not something that you can man, like not native to the terminal, we can go ahead and use -h or -help. It varies from program to program, but they'll often give up a set of arguments that you can pass. And so here we can also see the usage. That's how I knew that I needed to give it -i in the input file and -o in the output file. So if we wanted to rename all of our sequence identifiers, that first line, to something simple like numbers, we could pass a -r. So let's press up a couple times and get back to our what we executed, and let's just add a -r at the front and see what happens. Again, most things by default are going to overwrite files. So we already have an illumina.clean, but this is just going to overwrite it. Okay, so let's head illumina.clean. Okay, now look, this is a little bit simpler. We didn't need all that extra pieces of information. We just wanted a list of sequences in no particular order that had the actual sequence data attached to them. Okay, next I want you to try this on your own. with a new data set. This time it's some Nextera reads, and I just want you to use one half of the reads like we did previously. And so I'm currently Fastq dumping this accession number here, and you can go ahead and get that started as well. It'll take 5 minutes or so as well because it's a bigger data set. And we're going to go ahead and make a new adapter file as well, because I can tell you that there's adapters left in this sequence data, and it's a different sequence of adapters. So we're going to make a new adapter file called adapternex.fa for Nextera, and we'll use that to both trim and adapter clip our sequence data and then convert it to Fastq, and we should have something very nice. And along the way, we'll use Fastq to double check what we're doing. So I'll come back when this is done downloading. Okay, so we've got that file downloaded now, and we can confirm that it worked by going up here and seeing we've got that SRR155_1, which is the only one we're going to be working with, the forward reads right now. And as I mentioned, you should go ahead and Fastq this, both before and after we trim it. I'm not going to worry about that right now. You've got enough experience with that you should be able to do that on your own. But you should see that there is some remaining Nextera adapter content. And so the way to clean that up is with a different adapter sequence. And so I've provided what that is and how to kind of make a quick and easy adapternex.fa file that will contain that. So lastly, all we need to do is both trim and adapter clip these data and then Fastq them again, and you should end up with some nice quality data. So we can repurpose what we've already been doing with just different input file names. So SRR155. Notice I don't have to remember those numbers all the way because of tab completion. .fastq. Oh, we almost forgot. These are single end. And then we need to provide it the output. And I'll call it pretty much the same thing, clip and trim, because we're going to do both. .fastq. And if you can't remember how to spell those different commands, and that's fine, I always forget these things, we need to do the Illumina clip, but with a slightly different adapter file. So we need to go back and call this adapter nex, right? That's how we named it. And then finally, we want to do that sliding window. And if you didn't remember, you could scroll back and see that it's a window size of, let's say, 4 and a 30 quality. And let's hit enter. And so now it's going to go ahead and do our clipping and trimming. We dropped about a quarter of our reads, which in total was almost 100,000 reads. And then you could Fastq this. And take a look at it and see how nice it looks. But I'll let you go ahead and do that on your own. Okay, and I almost forgot that something I think we should do since you're working on really small servers, once you're done with the lab, is you should go ahead and clean up files that we're not going to use again, because you do have limited storage of only 30 gigabytes. So if you scroll down to the end of the lab, I've made some notes on things that you can safely remove or RM. Keep in mind, when you RM things, they are going to be gone forever. You don't get a second chance. It doesn't ask you if you're sure or not. So if we ls here, there's lots of sequence files that we're probably never going to use again. We could keep the HTML Fastq reports just if you want to look at them again at some point. They don't take up much space. But we want to get rid of anything that ends in .fq or .fastq because those are larger files. So let's use our wildcards and rm star.fq and star.fastq. Okay, now if we ls, we should have most of this stuff gone. So most of these things remaining are relatively small. The only other thing I want to mention is that when you look at where your SRA Fastq dump files go, they go into two places. So if we go to our home directory in ls, you see this NCBI folder. If we cd into that, there's a bunch of empty folders, but within the final level is the SRA folder. And within that, and type ls, we've got these caches as well as the SRA file itself. I like to just go in here, if I'm not planning on reusing these, I would just rm star within there. Or if you want to be a little safer, I would go star.sra and then rm star.cache. Okay, and now you've kind of freed up some space on your server. And lastly, you want to go ahead and stop your server. So always refresh your instance page before trying to stop it. Otherwise, it will refresh when you try to stop it, and you might turn off leave it running without realizing it. Okay, and that's it. Thanks.